Okay, in this lecture, we're going to continue to examine the evidence of superconductivity and see what we can learn from it. So we're going to begin by having a look at the thermodynamics of the superconducting state. Okay, so possibly a little bit of a reminder of some prelim thermodynamics here, although we've never done, I think, thermodynamics for magnetic materials before. So let's think about the Gibbs energy, okay, which is the internal energy minus Ts. Now, I don't need to think about any PV terms, okay, so I've got no PV type terms in this, as there's no structural phase transformation taking place. So no PV work is going to happen in this slide. Okay, so let's consider the superconducting state. Okay, so the Gibbs energy of this, so we'll call that GS. Let's say this is a function of the magnetic field we apply and the temperature that we're at. Okay, so we just need to think a little bit about magnetic work. Okay, so what we're going to do is we're going to move, so let's imagine we've got our magnet, okay, and here's our flux lines come out from the end of our magnet, okay, and we're going to take our little bit of superconductor and we're going to bring it into the magnetic field, okay. So the work done in moving a magnetic sample with magnetization M from somewhere where the magnetic field is B to somewhere where the magnetic field is B plus dB, okay, that's just equal to minus M dB. Now we just have to think about what that means. So if we had a paramagnetic material, M is positive in the same, it's in the same direction as B. So if I go from B to dB, so I'm increasing the magnetic field, I would be releasing work. Okay, the material would want to move there naturally. Okay, so I'd be lowering the energy. So that's where the minus sign comes from. Okay, so because this at the moment is defined as M is positive for a paramagnetic material. So if I then move, if I want GS at say B0 at T, that would be the Gibbs energy at zero field and the same temperature minus, I need to sum all these M dot dB terms up, so integral from naught to the field I'm interested in of M dotted with dB. Okay, so just to be clear that the B here is the applied field, external field. Okay, now the material is not paramagnetic, the Meissner effect. So if we consider the Meissner effect, then the magnetization perfectly cancels out the applied field. So mu naught M, I have to put the mu naught in to get the units right, equals minus B0, okay, because chi equals minus 1. Okay, so that's the Meissner effect. So if we do that, we will get that G0, GS at B0, and T is equal to GS at 0 and T plus 1 over mu naught, just substituting m in this formula here, integral from 0 to B0 of B dot dB, okay, which is going to be equal to GS of 0 and T plus B naught squared over 2. It's actually quite difficult for me to write just at the bottom of my screen because that's where my tablet puts my pen color selector. So I'm struggling very slightly here, but here we go. Okay, so that's B0 squared over 2 mu naught. So I'll put it over here. So this term B naught squared over 2 mu naught. What does this correspond to? So what this is saying is that if I've got my superconductor in no field, okay, and I move it to somewhere where there's field B0, okay, then that's moved it to a higher energy state. So B naught squared over 2 mu naught, this is the extra energy that must be somehow stored in the magnetic field around the superconductor, extra energy stored in field. And this is what you'd expect from a diamagnet because, we said that diamagnets want to move, they want to lower their energy, so they want to move from regions of high field to low field, and that's exactly what we're seeing here, that the system's got higher energy when it's in an external field. So, given its choice, it would minimize its energy, it would move to somewhere where the field is lower. Okay. Right, let us see how we can use that information. Now, first of all, I perhaps just want to remind you of the relationship we found earlier, or we noted had been found earlier, between the critical field, so BC, and the critical temperature. Okay, they behave like this. So the critical field is dependent on the temperature that we're at. Okay. Now, when the applied field is equal to B critical, so in other words, when I'm somewhere on the boundary of this phase diagram, it means the normal and the superconducting states are in equilibrium. Okay, so when B0 is BC, the normal okay. So what this tells us is that GS, BC, and T equals the Gibbs energy of the normal state. Okay, hopefully that notation is okay. BC. Okay, so in other words, when we're on this phase boundary, the free energy of the superconducting state and the normal state are the same. Now, how should the Gibbs energy of the normal state vary as we change the field? Well, remember that the normal state is probably only very weakly magnetic. The paramagnetic or diamagnetic susceptibility of the normal state is the order of 10 to the minus 5. It's really, really small. So let us, as an approximation, neglect that change. So if we neglect the magnetic behavior of the normal state, okay, if we do that, then Gn0 is equal to Gn BC. So in other words, the Gibbs energy of the normal state is not varying as we change the field. So that's interesting. So that what I can do now is I could relate the Gibbs energy of the, if I go back to the equation I had on the previous page, which involved the Gibbs energy of the superconducting state. So I take this one here. So if I take the previous equation, so the previous equation, just to write it out, so previously we had that GS B naught T equals GS naught T plus B naught squared over 2 mu naught. Okay, if I take this relationship, so what can I do now? So what I could do is if I took this equation here, and if I took B0 to be BC, so I just look at the critical field, I can replace this term, which is this one here, with this one here. But hang on, this one is the same as this one, so I could replace this term with this one. So that will give me Gn naught and T equals GS naught and T plus mu naught. Okay. Now, oops, sorry. This should be BC. Okay. Now this is interesting. So this tells me that the Gibbs energy at no applied field at a particular temperature is equal to the Gibbs energy of the superconducting state plus an energy that must be positive given by Bc squared over 2 mu naught. So if I am at any temperature, so if I was at the transition temperature, for example, then Bc would be equal to 0 and the Gibbs energy of the normal and the superconducting state are the same. It's kind of what we expect. But this is telling me that if I am at a temperature that is lower than this, okay, Bc is some positive number, and Bc squared over 2 mu naught, that's how much, that's the amount by which the superconducting ground state is lower in energy than the normal one. Okay, so superconducting state is more stable than the normal state when T is less than Tc. Okay, fine. Perhaps I've not learned a huge amount from this because we knew that it had to be a lower energy, but what we can do now is if we know the Gibbs energy, we can start to think about some of the other thermodynamic properties. So let me just skip through. That was another slide to write on. This is the same thing written out slightly. Okay, let's consider the entropy. Okay, so we want the entropy. Now, again, going back to just a bit of prelim thermodynamics, we know that the entropy is given by the negative of the change of Gibbs energy with respect to temperature. Okay. So what we would like to define is the change in entropy, okay, which would be the difference between the superconducting state minus the normal state. Okay, but we know that the change in Gibbs energy, so delta G, which was equal to GS minus GN from the previous slides, we knew that's minus BC squared over 2 mu naught. Okay, so delta S will be equal to, let me see, so we just need to, so this is This is G, and I just need to differentiate G with respect to T. And the minus signs are going to cancel. That's the first thing I'm going to see. The minus signs are going to cancel. And if I differentiate this with respect to T, I'm going to bring the 2 down. The 2's will cancel. I'm going to have BC over mu naught times dBc T. Okay. In fact, because B, we know that B is just a direct function of T, so that I'm actually okay to write this as dBc by dt, because there's no other variable. Okay. And again, if we remembered back to the graph that we had of how BC varied with T, okay, at TC, BC is equal to 0. So what we see from this is that at the transition temperature, delta S is equal to 0. Okay, so S is continuous, and this is the signature of a second order phase transformation. Okay, so there's no latent heat given out when we move into the superconducting state. Okay, so other thing we can notice is that delta S, so dBc by dt, this is a negative gradient. Okay, so BC by dt is decreasing, and so what that means is that delta S, the difference, the entropy, of the superconducting state is always going to be lower than the normal state. Okay, and that's what we find when we take experimental measurements. Again, if we back work this out from experiments, actually it's hard to measure the entropy directly, but if you were to, so here this is the normal state, and the red is the superconducting state, and you see at the transition temperature they're the same, and then the superconducting state, the entropy decreases. Okay, it's lower than what we'd expect in a normal metal, where we expect the entropy to just vary linearly down to 0. Okay. Again, that's the same thing written out. What can we really learn from this? Well, the entropy is always lower in the superconducting state. We know what entropy is, it's a measure of order. So that tells us that the superconducting state is more ordered than the normal state. It doesn't tell us how it's more ordered, it's just somehow more ordered. Okay. Let's then have a look at the heat capacity. Okay. So again, a bit of prelim thermodynamics. So heat capacity. So C is equal to T ds by dt. Okay, and we can define the change in heat capacity, which is the heat capacity of the superconducting state minus the heat capacity of the normal state. Okay, and just remind ourselves of the previous formula that we had. What did we have? We had that delta S was equal to 1 over mu naught BC dBc by dt. Okay, so plug that into that formula, and I'm going to get delta C is equal to, okay, the T stays out the front, 1 over mu naught. I need to do the product rule on this. Okay, so if I differentiate the second term, the derivative first, it will give me BC times d2BC by dt. And then I need to differentiate the BC term, that gives me dBc by dt. So I've got two of those multiplied together, so b dBc by dt all squared. Okay, now what happens at the transition temperature? So at Tc, well, we know that Bc is equal to 0. So that means that this first term goes away. Okay, so this term we can get rid of at the transition temperature, but not this term. Okay, this term is finite, and so what that means is that delta C at the transition temperature is greater than 0. So in other words, this is what we see here from the so this is the normal state, and this is the superconducting state. Okay, so what we've effectively shown is that when we are at the superconducting state, at the transition, there's a jump when we move from the normal to the superconducting state in the heat capacity. Okay, same thing written out more neatly. So that's interesting. What can we tell? Well, let's perhaps look at it from the other way around. So this is a sort of sketch version of what is actually experimental data that's observed for a lot of materials. And you notice that, yes, there's a jump in the heat capacity here, but then I get a sort of very rapid drop off. So quite quickly, the heat capacity goes down to essentially 0. If you look at it the other way, this looks very much like an exponential rise in the heat capacity. When do we get large rises in the heat capacity? You've done this in statistical mechanics, for example, when you had a two-level system. Okay, so this is what's known as a Schottky anomaly. You can have a defect, for example, some sort of two-level system. You get a spike in the heat capacity when the temperature is equal to, normally there's an excitation involved, and the thermal energy, so kT, is approximately equal to the gap, the energy of the excitation. Okay. So this data is really quite suggestive of the fact that the material must have some sort of excitation mechanism that becomes more active as we approach the transition temperature. Okay, so very roughly, we're sort of imagining that CV is somehow proportional to e to the minus some sort of energy gap over kT. Okay, now we know this energy gap must be pretty small because Tc is the order of a few Kelvin. Okay, so we're talking about some quite small energies here. But it does seem as if there's, in the superconductor, there's some sort of excitation mechanism that becomes available to it, so it can store a lot of an excessive amount of heat just before it moves into the normal phase.